Welcome to today's Explainer. I'm absolutely thrilled you're here, because honestly, we're tackling one of the most satisfying topics in computer science today. If you've ever sat there wondering how mere electrical signals and logic gates somehow magically transform into a fully functioning computer that can run software, well, this is where it all clicks together. We're breaking down Unit 3 of your computer architecture syllabus, specifically the foundational architecture of the central processing unit. So let's just jump right in and bridge that gap between basic logic and true computation.
You know, Units 1 and 2, they gave us the building blocks, right? We're talking flip-flops, multiplexers, basic logic gates. But how do those individual pieces actually coordinate to do something useful? Well, today, we are finally combining those raw components to build what Morris Monod famously calls the basic computer. We're going to see exactly how a real CPU operates and runs a program from scratch.
Here's our quick roadmap for this session. First, we'll look at building the basic computer. Second, we'll trace the fetch-execute cycle. Third, we'll scale up to a real CPU in stacks. Fourth, we'll dive into instructions and addressing. And fifth, we'll wrap up with the classic RISC versus CISC showdown.
All right, starting off with Section 1, building the basic computer. Let's look at the raw hardware components we need.
It's actually really fascinating how we translate human intent into machine action. It all comes down to an instruction code, which is simply a group of bits telling the computer exactly what to do. Take a look at the binary example here. It's broken into specific parts. You've got a 3-bit opcode on the left, that's the action, like LDA, which stands for load to accumulator. Then you have a 12-bit address field telling the computer where to find the data. So this specific binary string translates perfectly to load the data from memory address 5. Pretty straightforward, right?
Now, to pull this off, we need registers. These are the dedicated, super high-speed storage spots inside our basic computer. The PC, or program counter, is absolutely crucial. It always points to the next instruction we need to run. Then the IR, the instruction register, holds that instruction once we actually fetch it. The AC, or accumulator, does the heavy lifting for our math. And we also have the address register, data register, temporary register, INPR and OutTR for input-output, and the sequence counter for timing. But here's the cool part. They don't just exist in isolation. They all connect via a common bus system, tossing data back and forth to each other like a perfectly coordinated juggling act.
Once we have those registers in place, we need a vocabulary to speak to them. These are our computer instructions, and we can group them logically. Memory reference instructions, like add or STA, which is store accumulator. They interact directly with the main memory. Register reference instructions, on the other hand, like CLA to clear the accumulator, they only manipulate what's already inside the CPU itself. And of course, input-output instructions, INP and out, handle the flow of information to and from the outside world. That right there is the complete toolkit our basic computer has to work with.
But who actually conducts this whole orchestra? Well, that brings us to timing and control. That sequence counter we mentioned, it generates timing pulses, T0, T1, T2, and so on, giving the entire computer a heartbeat. Now, we can control the machine's actions in two ways. Hardwired control physically wires logic gates together to drive these pulses. It's incredibly fast, but it's totally inflexible. Microprogrammed control, on the other hand, stores instruction sequences in a special internal control memory, which makes it way easier to update or change later on.
Moving on to Section 2, the fetch-execute cycle. This is where we essentially turn the key in the ignition.
So the crucial takeaway here is that every single task a computer performs boils down to this one repeating loop. Step 1 is fetch. The program counter, let's say it's at address 5, goes out to memory, grabs the instruction sitting there, and pulls it into the instruction register. And crucially, the PC immediately steps up to 6, getting ready for the next round. Step 2 is decode. The CPU figures out what that opcode actually means. And finally, step 3, execute. The hardware physically performs the action. Fetch, decode, execute. Over and over and over again.
Let's make this super concrete with a memory reference example. Imagine we decode an add it instruction. Let's say our accumulator register currently holds the number 25. The instruction tells us to add whatever data is sitting over at memory address 12. If memory address 12 holds the number 17, the CPU pulls that 17, runs it through the arithmetic logic unit along with our 25, and boom, the new value sitting in the accumulator is 42. And it does this seamlessly, whether we're adding, storing data with STA, or maybe branching to a completely new part of the code using BUN or BSA.
But what happens if the outside world suddenly needs attention while we're stuck in this loop? Well, that's what we call an interrupt. Think of it exactly like getting a phone call. Our INPR flags, FGI for input, FGO for output, they signal that data is ready. Using an interrupt enable, or IEN flip-flop, the CPU politely finishes its current cycle, saves the program counter in memory so it doesn't lose its place, jumps over to answer the call by handling the new data, and then seamlessly returns exactly to where it left off.
All right, let's jump to Section 3, Real CPU and Stacks. Time to upgrade our mental model.
Let's see how a modern, real-world CPU builds on this Mano foundation. Our basic computer used a single accumulator design. That one AC register did all the heavy lifting for every single math problem. A real CPU organization, however, uses multiple general-purpose registers. So instead of bottlenecking at one single accumulator, a modern CPU has a whole bank of registers communicating across a complex bus. This allows for way more sophisticated and, frankly, much faster data manipulation.
Another massive upgrade you'll see is stack organization. A stack is basically a last-in, first-out structure. Think of it like a stack of plates, and it is absolutely perfect for evaluating math. Normally, humans write math as an infix equation, right? Like open parentheses, 3 plus 4, close parentheses, multiplied by 2. But CPUs, they love postfix, also known as reverse Polish notation. We convert that equation to 3, 4 plus 2 times. Now watch how smoothly a stack handles this. We push the 3, we push the 4, the CPU sees the plus sign, pops them off, adds them, and pushes the 7. Then we push the 2. The CPU sees the multiply sign, pops the 7 and the 2, multiplies them, and pushes the final answer, 14. It is so clean, elegant, and insanely efficient.
Okay, Section 4, Instructions and Addressing. Basically, how do we locate our data?
Notice how we can actually shrink the exact same calculation, like x equals a plus b, depending entirely on our architecture. If we have a complex 3-address CPU, the instruction has to be written out fully. Add a and b, store the result in x. In a typical register CPU, it's a 2-address format. Add b into x. In our basic Mano computer, which is 1 address, we just say add b, because the accumulator is always automatically assumed to be the other half of the equation. And in a stack CPU, we don't use addresses at all. It's a 0-address format. We literally just issue the command add because it knows the operands are already sitting right there on top of the stack.
Now, when we do use addresses, how does the CPU actually find the data in memory? It uses addressing modes. Sometimes the instruction contains the actual data itself. That's called immediate mode. Sometimes it points directly to the data, but often it's a bit more complex. Take index addressing, for example, which is phenomenal for arrays. Let's say our base address in memory is 300, and our index register currently holds 20. The CPU computes an effective address of 320. It literally does this math on the fly just to figure out where to pull the data from.
And as the CPU runs all these calculations, it constantly needs to make decisions. It does this using program control flags that sit inside a status register. Like, did the last math operation result in a 0? Boom, the Z flag flips on. Did it result in a negative number? The sign flag flips. Was there a carryout or an overflow? These flags are essentially condition codes. They allow a program to branch and make logical choices, like, hey, if the result of that last operation is 0, jump to this entirely new section of code.
Finally, we arrive at Section 5, RISC versus CISC, the ultimate architectural showdown.
On one side of this massive industry divide, we have reduced instruction set computers, or RISC. Think about the ARM processors inside your smartphone. The philosophy here is simple, done fast. They use small, fixed-length instructions that execute in a single clock cycle, heavily relying on pipelining and lots of registers. Now, on the other side is complex instruction set computers, or CISC. Think of the Intel x86 processors running your laptop. Their philosophy is powerful, done flexibly. They use larger, variable-length instructions that can handle complex memory addressing in a single multi-cycle command. It's two completely different paths to computation, but both have been wildly successful in the real world.
Which brings us to a final, slightly provocative thought to leave you with today. We've just mapped out the anatomy of a machine. We've seen how Mano's basic computer bridges the gap from simple logic gates all the way up to a system that can fetch, decode, and execute instructions. But if this theoretical fetch-execute cycle runs literally every computer on Earth, how does it physically look stamped onto a real piece of silicon? How do the pins, the physical voltages, and the registers actually align in a real hardware chip? Well, that is exactly what we're going to uncover in Unit 4 when we get our hands dirty with the legendary 8085 microprocessor. You definitely won't want to miss it. Thanks for hanging out with me for this explainer, and I'll see you next time.